Well, without further ado, Ryan's going to talk to us about discretizations and multigrid solvers for problems related to fluid flow. Over to you.
All right, thank you guys very much. In case you don't know me, my name is Ryan Grove. Thank you very much for inviting me here. At least in my opinion, it's been a big success so far because we've figured out lots of cool things about the melt analysis that we didn't know before, and we're going to share that with you today. So topics of this talk. First, we're going to talk about the three-field form melt analysis, and then if we have time, you can see there's 61 slides. So I'm going to try to go slow and explain everything. If you guys have any questions at all, so if at any time you get confused, please ask questions as we go. If I can't answer them, hopefully Timo and Juliana can. So the big questions we seek to answer in this talk is what discretization should I be using for the three-field form, and then why should I care about geometric multigrid? All right, so motivation behind this. Melt generation and migration are important processes for the evolution of Earth's interior and impact the global convection of the mantle. While they have been the subject of numerous investigations, the typical time and length scales of the melt transport are vastly different from global mantle convection, which determines where melt is generated. And this, of course, makes it difficult to study mantle convection and melt migration in a unified framework. All right, so let's talk about the derivation. This comes from Juliana and Timo, and they were motivated by Keller et al. So we're going to incorporate the solid and fluid phase in material based on a melt fraction we're going to call phi. And then so we have this equation right here. Now we're going to use the Mackenzie equations and Darcy's law to eliminate fluid velocity. And then we're also going to introduce compaction pressure, which depends on our phi that we stated above, our melt fraction. And then we're going to get this equation that we're going to talk a little bit more about on the next slide. This is pretty much the same exact slide that Timo talked about when he gave his talk. All right, so the model that we're going to conserve ourselves with. So we're going to look for a solution, velocity, fluid pressure, compaction pressure. And these are the equations that we will be using. So, yes?
It should be the symmetric gradient of u inside that. Give the beta.
So instead of using symmetric gradient, we're using the Laplacian to make the analysis easier?
Okay, all right. Sorry.
Is that the correct way of saying that? Okay. So eta is going to be the shear viscosity. Kd, as we call it, is our Darcy coefficient, and 1 over epsilon, epsilon is the bulk viscosity, and we're going to assume 1 over epsilon is greater than 0. Also, for the analysis, it's so we can recover Stokes if Kd is equal to 0. All right, and then note, although eta and 1 over epsilon are not constants, we are going to assume they're bounded, and therefore we have a minimum and a max for each one. Okay, so some assumptions in order for us to do our analysis. We need the velocity to be 0 on the boundary, this condition right here. We need the fluid pressure to be mean 0 throughout the domain. And we also need a boundary condition, which we do right here. So you can pick multiple boundary conditions. We do this one to make the analysis easier.
So is the important thing that it's like a Dirichlet function or
I think yes. Yeah.
It doesn't matter if it's 0 or not, but yeah.
Okay, and so as you can see from up here, we're going to split this into cases. And why are we going to split this into cases? So in our analysis of the three-field form, we found that a vanishing Kd changes the nature of the PDE that we have. So we're going to split up our analysis into 3 cases. First, we'll look at when Kd is 0 everywhere, then when Kd is greater than 0 everywhere, and then at the end, we're going to talk about what if it's both, what if it's 0 some places and non-zero somewhere else. So like I said, first case we're going to look at is Kd equals 0. So that's basically saying, hey, we have no melt at all. And we expect that we could recover Stokes flow of the solid both analytically and computationally. So let us derive this down. So we're going to let our phi slash Kd equal 0. And we're going to reduce the equations I showed you to the following. And then since we know that the compaction pressure is equal to the solid pressure minus the fluid pressure, we get the following form. And when there is no melt, H is typically 0, and we can say that PS is equal to PF. So the updated model that we get down to is we have Stokes. So it's important that we talk about spaces for a little bit. We want U to be in H1, 0. What does that really mean? It means we're going to pick U to be in the H1 space, but we need to make sure that the velocity on the boundary is 0. And then our fluid pressure, we're going to put in L2 star. And the reason I call it star is because there's a few things that we need to make sure happen. We're going to say it's in L2, but like I said, it needs a boundary condition, and it needs that the mean value is 0. All right, so this reduces our equations down to these guys, since that we were able to take PC equal to negative epsilon h from equation 3. All right, so we're going to take a quick break to talk about imp soup conditions, because they're very important for this case. So we can rewrite our Stokes system as follows into a bunch of bilinear forms on the left side and equations on the, functions on the right. And this is well posed. And what do we mean by well posed? It means we have existence, uniqueness, and bounded by data, if and only if we have this imp soup condition. So I don't like to focus on this condition written in math form so much. Let's talk about what it actually means. So we can interpret this as instructing us that we must take care to choose our velocity space so that it's large enough so that our system is stable. So if this condition is not met, our fluid pressure will be nonsense. If you don't believe me, stay tuned, I will show you. In other words, our discrete Stokes system is stable if this imp soup condition holds for particular choice of discrete spaces if you pick a stable element pair. An example of that will be Taylor-Hood elements, which we will talk about later.
Can I ask a question?
Yeah.
Could you go back 2 slides? Next one. Go back one more. Yeah. One more. Yeah. So you prescribe Dirichlet conditions for velocity everywhere on the boundary for both the normal and the tangential components, right? So why do you need to specify PF as well? Because in your variational form, you would have normal stress, like total stress dotted with the normal should be specified. But if you prescribe velocities everywhere, and you haven't kind of split that total stress into a deviatory part and the pressure part, I don't really understand why you need to specify grad P dot n equals 0.
I forget the exact spot.
Do you understand what I mean?
Kinda?
Kinda.
I forget the exact spot in the derivation, but I know in Juliana and Tima's paper it was a requirement. Do you guys remember?
You've got 2 velocities in this. You've got the solid velocity, which is being pinned down by that u equals 0. The other one is you've got to say something about the Darcy flux. You've got to say something about the fluid velocity, and that's what that dpdn, or so grad pf dot n.
But this is just Stokes.
Yes, so technically this is the reduced form, and I don't think you need the...
Oh yeah, once
Grad
you've gone
P dot
down
n
to Stokes,
equals
you're right, you
okay.
lose the boundary condition.
Yeah, okay. But in
Yeah,
the other
when we go
case,
down
you
to
need
the-
In the other case, yeah, I just didn't understand
okay.
here why you needed
Yeah, I think you can do it with L2 here.
condition.
I think that's a
Okay,
good
mean
point.
0.
Yeah.
Okay, sorry.
Okay. Good question. We were here. All right, so we're not going to talk too much about the analysis of showing that it's well posed. Basically, if we have that imp soup condition between our spaces x and y, and if you remember, x was my space for my velocity, y was my space for my fluid pressure. If you have an imp soup condition between them, then you have well posedness of the system I showed you. Similarly, we also have discrete well posedness. Just a few things to talk about here. We're going to let xh and yh be finite element spaces that are discrete approximations of x and y by piecewise polynomials. So, like I said on the last slide, assuming that we have an imp soup condition between xh and yh, we also have well posedness in the discrete sense. Right, and then introduction to finite element spaces and convergence orders. This is just in case you're not really familiar with this kind of stuff. So a finite element space Qk uses tensor product polynomials defined on each cell of degree k over quadrilateral meshes. For those of you who use Phoenix, it's analogous to the pk spaces that you use there. So we say that a sequence converges with order q. This is moving on to the convergence order side. Converges with order q to its limit if this is true. So you're going to look at your current iteration minus the limit, the norm of it, over your previous iteration minus the limit, the norm of it, and then you're going to get some q here. And then depending on what that q is, tells you your order of convergence.
This is not the same K for the polynomial order, right?
No. No, sorry. Could probably change that letter probably. All right, so in particular, convergence with order q equals 1 is linear convergence, q equals 2 is quadratic, etc. I'm going to refer to linear, quadratic, and cubic when I get to my computational results, so I just wanted to make sure everyone knew where I was coming from. But now let's talk about the convergence. So let's start with our velocity bound. So we're going to go through a lot of the analysis here on these first few slides in this case, and then in the later cases we'll kind of skip through some of the analysis. All right, so we're going to decompose u into a u hat and a u naught. And we do this so that as long as there's a solution to this problem with our u naught, we're able to do our analysis on u hat over this problem. And you see that the only real big thing we accomplished was making this have divergence 0, which helps us out a lot. All right, and then let's look at the continuous and discretized weak forms of the previous equation. One big thing to note is that when you have this discrete fluid pressure and you're going to multiply it by our test divergence of VH, we have that it's 0. Therefore, we're able to reduce things down quite a bit. And if we restrict this equation 11 to be in our discrete space with a VH and subtract 12 from 11 and let E equal u hat minus the discrete approximation of u hat just for nice bookkeeping, we get this equation right here. So that was a lot of steps in one. Feel free to ask questions if you didn't follow anything. And then we're going to decompose E even further. So we're going to pick a WH from our discrete approximation of our X space, and we're going to say u hat minus WH plus WH minus UH hat. And we're going to call this, oh, I always get this letter wrong. Someone help me on the letter. Nu plus VH. All right, so note that VH is in our capital VH space, and thus what we talked about before is still true. We still have that the QH, when with a test function, divergence of VH is still equal to 0. All right, so then if we're coming to the point where we get to choose what we want our VH to be, and you always want to choose it so that your analysis is easiest. So we're going to pick it to be VH, and therefore we're able to write this equation right here. And we wanted to do that so that this works out really nice. So, oh, no, I'm sorry. We want to do that so we can look at this so something else works out really nice. And basically, we just want to show that this is bounded by a constant times this plus eta 1 times that. So keep this in your mind. The only reason we wanted that to really work out well is so that when we look at our velocity bound, we are able to plug that in for this part right here. And then why that was so nice is because now we have this term basically twice, and we can put them together. When we do that, we get that it's less than or equal to all this stuff, and let's go take our attention down to the bottom, and the important thing to take away from this is we get h to the k for the velocity and h to the L plus 1 for the pressure for the velocity bound. Yes?
Could you point out when you go on through the derivation which step you actually needed to make or replace the symmetric gradient with just the gradient of u? Right, in the beginning, like John's question, he asked, why did you have grad u rather than symmetric gradient?
Right.
I don't see yet where you had to make that simplification to make the analysis possible. I mean, when you get to it on the slide, maybe you could just show me that this is the bit that caused the trouble. Because so far it looks like it should all work with just symmetric gradient.
It may be the case that it does. Do we have a...
I don't know off the top of my head how to do it. You kind of want like an H1 norm, which does not have the symmetrized gradients in there. I think you assume enough regularity that they're the same.
I was just curious.
Yeah, I don't know. Good question.
All right. And then in this last inequality, we had to assume that our XH space and YH space were QK and QL. All right, similarly, we could go through the convergence for the pressure bound, but what you end up with is H to the L plus 1 and H to the K. All right, so why do we even go through all this? Why do we care? It's because if we combine the two bounds together, we can get lots of useful information out of it. So we're going to enforce K minus 1 is equal to L. And if you remember, we talked about the IMSUP condition. This is just making sure that the IMSUP condition is satisfied. So this itself is enforcing a Taylor-Hood element pair. So we're going to obtain that the order of convergence of the error between the exact solution and our calculated solution for U in the L2 norm is K plus 1, U in the H1 norm is K, and then PF in the L2 norm is L plus 1, which is also equal to K from this right here. All right, what does that tell us? If we choose Q2, Q1, Q1, we would expect convergence orders of 3, 2, and 2 in the L2 norm. And you might ask yourself, well, what if we picked Q2, Q2, Q1? Well, that does not satisfy our IMSUP condition, so we really don't know what to expect here. We don't know that it won't not work, if that makes sense, but, but we really just don't know what we're going to get from it. So just a general, these are the expected convergence rates. We're going to go into the numerical results soon, but keep in mind that when KD equals 0 for Q2, Q1, Q1 elements, we do expect 3, 2, 2 in the L2 norm, and for Q2, Q2, Q1, we don't really expect anything. All right, this is the test problem we're going to use for the entirety of this section of the talk, the whole entire three-field form meld analysis, with the exception that we'll change this KD eventually. But our H is going to be 1. This is a little complicated. U is picked to be divergence free, and then our pressures are just signs. All right, and then I'm going to show you guys a bunch of cool plots. But first, I wanted to put a plot information slide so you're not spending half the time being like, I wonder what this cool plot means. So what we have here are basically plots of convergence orders. And what you want to focus on is if things are aligned with this red line, they're going to be linear. Green line, quadratic, blue line, cubic. As soon as I switch to the next slide, all these colors are going to change to confuse you, but just look at the legend. And then the cell diameter is shown on the x-axis, and the error between the exact and calculated solution for a particular variable will be on the y-axis. Right, so plot 1, the computational results for the velocity. So what do we see? If you look here, like it's kind of covered, but we have Q2, Q1, Q1, and Q2, Q2, Q1 elements, and they both happen to fall on the same exact line. So for velocity, we see cubic convergence for both Q2, Q1, Q1, and Q2, Q2, Q1. Yes?
All L2, all the errors are measured in L2. Yeah.
Yes, this is all L2. Thank you. All right, but now let's look at PF. This is where things start to get interesting. If you look at Q2, Q1, Q1, it's just hidden here, somewhere in this quadratic convergence. That's nice. But if you look at Q2, Q2, Q1, it's just way up yonder and not very right at all. And definitely not converging. Okay, so what should it look like? So if you run our test problem and you try to visualize PF, if you have Q2, Q1, Q1, you get something that looks like this. It's a nice little pretty piece of some sign thing. If you try to visualize it for Q2, Q2, Q1, just kind of goes poof. So this is a really big number. This is a really, really tiny number. And it's just kind of oscillating between the two. All right, and then lastly, we're just going to look at the computational results for the compaction pressure. And you can see that both of them are along right here, and they're both quadratic. So let's look at a summary. What we expected for Q2, Q1, Q1 was 3, 2, 2. And what we expected for Q2, Q2, Q1 was we didn't really know what to expect. We just didn't expect it to work. And what we actually got for Q2, Q1, Q1 was 3, 2, 2. So that's great. That's what we wanted. Good for us. What we got for Q2, Q2, Q1, on the other hand, was a 3 for the U and a 2 for the PC, but the fluid pressure did not converge. Right. Any questions on this part?
I mean, can you remind me? So is PC effectively the solid pressure in Stokes way, and PF, or was it the other way around?
PF is effectively the solid pressure in fixed flow.
So you've calculated accurately something you don't mind about, and you're not calculated accurately something you do care about.
Yes. Yeah, is that a good?
So you compute PF and PC, and PF is nonsense. And if you wanted the solid pressure back, you need those two to compute your PS. And
But in this case, P is 0 anyway, so the compaction, like we don't, like PF should be PS.
sure.
Okay. Any other questions on case 1? Then let's start looking at case 2. So introduction to case 2, we're going to turn our attention to the case where KD is always bigger than 0, or in other words, there's melt going on absolutely everywhere. In this case, there's no need for an in-suit condition, and thus different finite element choices can be made and be successful. All right, so our updated model, U is going to be exactly where it was before in our H10 space. The fluid pressure now has to be bumped up to an H1 star space. So this is where we definitely need these terms, and I think I agree with you guys that we could have did it just in L2 in the case 1. And then PC is going to just be an L2. All right, and then if you multiply with our test equations and you integrate by parts and balance derivatives, this is the equations we'll be looking at for case 2. Right, first thing I want to show you guys is the energy norm we're going to be using. So we're basically just going to make it the square root of all the individual norms added together with their constants inside. One notable exception is that we add in this PFL2 norm so that we keep control of PF even if K equals 0, which doesn't necessarily matter in this case, but it will if we ever try to go into case 3.
Why did you choose that?
So that's complicated.
I mean, there's physical reasons for some of it, yeah? Most
Yeah.
of it would be shear dissipation.
So my first idea was not including this one, and then we were talking with Maxime, I don't know his last name, so I don't want to butcher it. And
Oh, it's not got the grad in it.
Root square.
Actually, yeah, no.
No, it's squares of all the norms, and then you take the square root. And it's the H1 semi-norm on the left, so there's a gradient view.
Oh, so there is a
The
gradient.
first one
view
is
in
gradient view, the
Yeah.
second one is PF, the third one is gradient PF,
yeah, so
and the
these
last one
ones,
is PC.
Oh,
these
yeah,
ones
you
are
gotta take
H1
into account all those
seconds.
indices down the bottom.
To answer your
Okay,
question
yeah.
so that the analysis goes through.
So the answer is before.
But,
But you
so it's a
like to-
combination of the energy norms of the normal spaces. So you have H1 for velocity, and the standard energy norm is the H1 semi-norm. That's what you
Yeah,
do the
okay.
analysis in.
Okay.
But is there any reason why it should look a bit like that, the viscous dissipation? Okay.
I don't know.
Okay.
all right, so this is the energy norm we're going to be using. Let's look at our bilinear form. So we're just going to take all the left-hand sides of the equations I showed you guys, the new updated model for this case. And we're going to stick them all together. Important thing here, we do not flip the sign on these two terms. So we no longer have a saddle point problem. And this gives us coercivity. We don't need an in-suit condition, all sorts of nice things. All right, and then this is where we found a book from, or a theorem from a book from Brezzi. I don't want to say that wrong at all. And basically, if we're able to prove these two conditions are true, then we have well-posedness as long as W is a Banach space, B is a reflexive Banach space, and we have A is a linear continuous linear form, and that F is continuous and bounded, linear and bounded, sorry. All right, so to save you through all the analysis that we kind of went over in case 0, we were able to show continuity and boundedness. Basically, you just need to make sure this right here is less than or equal to some constant times our energy norm for UPFPC times our energy norm for VQFQC. And we needed the bounded linear right-hand side. All we really needed to show was that F was less than or equal to some constant times our energy norm of VQFQC. And the other conditions I talked about,
So that concept
yeah,
became large when KD is small, right?
yes. So you can kind of foreshadow into the future of the case where we try to include KD equals 0. And you can see the problems we're already going to run into. And then the other two conditions we also showed, we constructed the first condition a similar way, but they are analogous to each other. And then on to the important part that we really want to look at. What's our convergence and link convergence rates that really affect what we want to choose? So we're trying to get a bound on U minus UH, P minus PH, where P I just have written as PF comma PC, just to try to make things fit. So we end up finding this bound right here, but instead of talking about that, let's just jump to what it kind of means. It means that we can bound our energy norm by some constant times H, and then the min of K, L plus 1, L, M plus 1. Alright, so what does that really mean? That means if we're going to pick for our discrete spaces QK, QH, QM, that we can pretty much see what our convergence rates should be. Like, what do we expect? So for example, picking the Taylor-Hood one that we picked before, the stable one, Q2, Q1, Q1, we would expect convergence orders, so minimum K, which I said 2, 1, 1, so we have a 2, a 2, a 1, and a 2. And the minimum of that would be 1. So if we use Q2, Q1, Q1, we can only expect 1, which means 1 in the H1 norm for velocity, 1 in the H1 norm for pressure, and 1 in the L2 norm for compaction pressure. So that means we only expect rates in L2 of 2, 2, 1 for this particular case. And then if we did Q2, Q2, Q1, this no longer drags it down, so you would have 2, 3, 2, and 2, yes? So therefore the minimum is 2, and we would expect 3, 3, 2 in the L2 norm. So instead of you guys just trying to picture in your head what I just said, let's look at a table. So this is our expected convergence rates. So like I said, if we pick Q2, Q1, Q1, we expect 2, 2, 1. And if we pick Q2, Q2, Q1, we expect 3, 3, 2. And why do I have these in orange? It's because they're suboptimal. The best we can hope for picking Q2, Q1, Q1 would be 3, 2, 2. But we're only expecting that we're going to get 2, 2, 1. Alright, so this is just a reminder of the test problem in case you forgot. So for these ones, we decided to take KD equal 1. Alright, so let's look at our computational results for U. Using Q2, Q1, Q1 elements, we're able to see quadratic convergence. And using Q2, Q2, Q1, we're able to see cubic. For fluid pressure, same exact situation. For Q2, Q1, Q1, we see quadratic convergence, and Q2, Q2, Q1, we see cubic. And then our compaction pressure, both quadratic. All right, so let's summarize what we found. So what we expected for Q2, Q1, Q1 elements was to get rates of 2, 2, 1. But what we actually found in practice was 2, 2, 2. But what we expected for Q2, Q2, Q1 was 3, 3, 2, and we were able to see that in practice. All right, so in conclusion, so this is kind of combining case 1 with case 2. We see that for Q2, Q1, Q1, when KD equals 0, we get the optimal convergence that we expected, and we get the same thing for Q2, Q2, Q1 when KD is greater than 0. But here we don't see what we want, and here this 2 is a little suboptimal.
Doesn't your analysis just tell you what to expect for UP measured in that particular norm, right? You had it as H to the power mean of stuff.
So like the H1 norm.
Yeah.
And then you can use an inequality, is it Niche's inequality, to get a norm
Individual pieces. Okay.
for the L2 norm. Yeah, good question. I had that same exact question a few days ago. So
I just wondered what the leap was to go from the slide
Mhm.
2 slides ago and then
Mhm.
the expected stuff here.
Yeah. Good. I'm glad you asked that. All right, so now we talked about our conclusion. Let's talk about case 3 where KD is greater than or equal to 0 in future work. We've been trying to find something to let us analyze KD greater than or equal to 0 for a while now. And you guys kind of already saw where we run into the problems. You get 1 over KD min. So if your KD min is 0, you just get an infinity, and most of the proofs tend to explode at that point. So we're having a lot of trouble figuring out that part, but it's what we plan on working on next and what we're actively working on right now. Our suggestion, if you are just going to do it, is to use Q1 or Q2, Q1, Q1 elements because they're stable no matter what, even though you'll get suboptimal rates. This is what's done in Aspect right now. Also, this is another future work type of idea. You could pick Q2, Q2, Q1 if you added some kind of Galerkin least squares term or another stabilization term. This is something we definitely plan to try out. And then lastly, you could just use a different formulation. Don't use the 3-field form. And speaking of future work, we definitely have enough time to go over this multigrid stuff. Happy about that. So this is something I did before I came here. This is work on geometric multigrid for Stokes system. And the idea why it matters, why I'm talking about it, is that eventually we plan on, or maybe not me, but someone will plan on putting it into Aspect so that we have geometric multigrid. And then I will show you why that is something to be excited about. So this is the same solver slide that Timo used, and Timo and Juliana are going to talk about it more, so I'm not going to focus on it too much. Let's look at Stokes' system of equations. So here we just have our standard Stokes. U is going to be the velocity, P is the pressure, F is the external forces, and we have our symmetric gradient. And let's just talk about a Schur complement real quick. So the weak form of the discrete equations naturally leads to the following linear system of nodal values. We get this. An approach one may try to solve this system of equations is by forming your Schur complement. So what does that mean? First, you just want to find the solution P of this equation, and then you want to plug it into this equation and then solve for your velocity U. All right, so block Schur complement preconditioner. An alternative to what I just said is to attack the block system all at once and use an approximate Schur complement as an efficient preconditioner. So the main idea is as follows. We find a block preconditioner P such that the matrix, this guy, is simple, and then an iterative solver with that preconditioner will converge in a few iterations. So using the Schur complement, which is just B A inverse B transpose, you can find what your P inverse is. So notice that A squiggle, S squiggle are just approximations for A and S, and the P that we will be using is this matrix down here. Well, matrices multiplied together. All right, so let's talk about some linear solver and preconditioning issues. The plan is to solve A, B transpose, B 0 using GMRES with this preconditioner, but we don't actually have A inverse or S inverse, nor do we want to solve for them. That would defeat the whole purpose. It'd be really expensive to do. So we're just going to approximate them. And for the slides that we're going into, we're just going to say it's with a bar.
Why do you prefer the lower block triangular form as opposed to the upper? Yeah. Maybe I just didn't see the equation correctly. Oh, yes, inverse. Okay. Yeah, sorry.
Yeah. So when I originally wrote these slides, I had it as lower, and then I had to change it to upper, and that made me nervous that I didn't do it right. Okay. So we have to approximate A inverse and S inverse. So the Schur complement is going to be approximated by a pressure mass matrix, which is simple since the mass matrix is always well conditioned. And then when we precondition with the mass matrix on the pressure space, we only need a few CG iterations that are basically independent of the mesh size. And on the other hand, when we look at A inverse, we need to use either IOU or geometric multigrid. So let's talk about multigrid real quick. So as a solver, this approach has the advantage over other methods that it often scales linearly with the number of discrete nodes used. So a multigrid method with an intentionally Reduced tolerance can be used as an efficient preconditioner for an external iterative solver while retaining the O of n time. So this is the big takeaway of multigrid. We get this O of n time, and this is the main, why should I care about geometric multigrid? So multigrid overview. So what happens in a typical multigrid V cycle? So simple iterative methods tend to damp high spatial frequency errors fast. So after a few smoothing steps of a simple method, we're going to map the current error out onto a coarser grid where the errors will have relatively higher spatial frequency there. Then we're going to take a few more smoothing steps of a simple method on the coarser grid, then continue mapping to coarser grids until the grid is coarse enough to solve. Then we'll solve and interpolate back to the next finer grid and do a few smoothing steps, and then continue to the finest grid. So let's look at a picture and explain that again. So we're going to start up here. You don't want to solve up here. Your mesh is just too fine. So you're going to restrict down to a mesh below, do a few smoothing steps, and continue this process till you get down to a coarse enough mesh that you want to solve on. You solve there, and then you prolongate it up, prolongate the residual up, and then you do a few more smoothing steps so you get back up to your finest mesh where you will have sent your correction to. Alright, so why do we care about this? So for IOU, if we're doing this in DL2, so the setup time, so right here where it says GR, it should just be saying your global resolution, or global refinement, sorry about that, global refinement level. So if we have 3 initial global refinements, the setup for IOU is 0.084 seconds, the solve time is 1.256, and if you look at geometric multigrid, we see that the setup time is 0.37 and the solve is 1.04. So it looks like IOU is beating us by a little bit of time. At the beginning, you're like, oh, whoop-de-doo, we didn't really gain too much. But if we skip down to 5 global refinement levels, we see that the setup time is about 30 seconds and the solve time is 150. But for geometric multigrid, our setup time is about 21 seconds and the solve time is half of what it was for IOU. And we can see that this is scaling linearly, but this is not. And this is good because as soon as you get even more global refinements, so say you have 7 or 8 initial global refinements, this is still keeping its linear scaling, whereas this kind of blows up. All right, so let's look at the iterations. So as you're doing your global refinements, if you look at the iterations of your solvers, for the outer iterations, they're getting bigger for IOU. The inner for A are getting bigger for IOU, and the inner for S are getting bigger for IOU. But if you look at the geometric multigrid ones, they're all staying about the same. All right, so in conclusion, as can be seen from the previous slide, the number of iterations for A increase for IOU with refinement, leading to worse than linear scaling and solve time. In contrast, the number of inner iterations for A to stay constant with geometric multigrid, leading to nearly perfect scaling and solve time. Thank you guys very much. These are my references that I used. A lot of you are in this room. Well, I guess Sander is in here. But does anyone have any questions?
Thank you. Questions? So going back to this issue of the symmetric gradient, I mean, where would it come into the analysis? I mean, do you have any feeling for where it would come in?
I'm not sure. So I did the analysis with Laplacian, not even thinking about symmetric gradient, and then we just never did it for symmetric gradient.
Right? It really matters that it's a symmetric gradient.
Yeah.
Put into the test problem. Sorry? Yeah, into the test problem.
Yes, in your test problem, actually. What problem did you solve?
D2 is 1, right?
What?
Yeah, are you solving the one that you write when you solve it? Or, yeah.
Let's say, hold on, let me.
The computations were done with a symmetric gradient, but the viscosity was 1 in this example. Sorry, in these examples.
Yes, yeah.
Okay, so
But I think we.
oh yeah, so eta is 1 and then it doesn't matter. So if you had a
Yes.
spatially varying eta, then
Oh.
you'd start running into.
Yeah, but we solved this both with the Laplacian and the symmetric gradient to get similar results. But we did check both in our calculations.
Yes, okay, so you numerically computed both ways, and in this case you get exactly the same results because eta equals 1. As soon as you have a spatially variable eta, they should be different.
Mhm.
I think that the symmetric gradient makes the proof of the coercivity much easier.
Makes it easier.
Oh no, sorry. Harder.
Harder.
So
I was going to say, then why did I do that?
Symmetric gradient, you have to use the coercive inequality. But in this analysis, you haven't talked about the coercivity issue. So I personally think that helped using the gradient instead of the symmetric gradient, helped the proof of the coercivity.
Thank you for that info.
And that's what it does.
Any further questions? In which case, can we thank Ryan once again? Thank you.